Okay, so I guess we'll get started. I hope you all doing well. Let me screen share. All right, so today's lecture is going to be a little bit more intense. It'll maybe run over by like 10 minutes. So we'll try to save our questions until the end, just so we can make sure to get through everything. Yeah. And so without further ado, if you can't hear me at any point during this, just unmute yourself and yell at me or something. Okay, so today we're going to be talking about solvents and solvolysis reactions. So we've kind of alluded to this throughout the week in both your homeworks and the study groups. And so today we'll get a more formalized introduction to the concept. Okay, so our learning objectives. So first, we're going to start with classifying solvents into protic versus aprotic, donor versus non, and polar versus nonpolar. And then Brendan's going to finish it with solvolysis reactions. Okay, so the first thing we're going to do is we're going to kind of classify these solvents. And there's three ways that we're going to be looking at it. The first is going to be kind of the protic versus aprotic. Two is going to be the Lewis donors versus the non-donors. And then three is going to be the polar versus non-polar. And so these kinds of solvent classifications are going to play a role when we look at our kind of determining between SN1, SN2, E1, and E2. So let's start with the first one, the protic versus aprotic solvents. So protic solvents are good hydrogen bond donors. And some examples of these include things like water, basic alcohols. I cannot spell. Okay, basic alcohols, things like methanol, propanol. We've also have our carboxylic acids, COOH. And so if you remember, right, hydrogen bonds are formed when we have a hydrogen bonded to atoms such as fluorine, oxygen, and nitrogen. And when you have these bonds, because of how electronegative these atoms are, this hydrogen is going to develop a partial positive charge, and then it can do these hydrogen bonds with what we are going to call as H donor acceptors. Right, so that should just be a review of what you already know about hydrogen bond donating. And so the second part of protic versus aprotic solvents are going to be our aprotic solvents, right? These are solvents that don't have any hydrogen bond donors. So you might have hydrogens in your solvent molecule, but those hydrogens are not going to be connected to these fluorine, oxygen, nitrogen, to these electronegative atoms. So we won't have any possible hydrogen bond donation. And so this is going to be important because protic solvents are able to stabilize anions. And so let's draw out what that looks like. Imagine we have some kind of halide, and then we have just some generic alcohol. Something like that. And so our oxygens are going to be partially negative with our hydrogens as partially positive. And so what you can imagine is based on what kind of halide this is, we're going to be forming either hydrogen bonds, or we're going to be forming these kind of dipole-dipole interactions. So if this is something like Cl minus, we would be having our dipole-dipole interactions. And if it's something like, I don't know, bromine, that'll be, oh, sorry, not bromine. it's something like fluorine. That'll be our dipole hydrogen bonds. So if it's Cl minus, that'll be our dipole-dipole interactions, and if it's fluorine, that'll be our hydrogen bonds. But the bottom line is that these protic solvents are able to stabilize this negative charge that we form. And so when we talk about solvents, a word that you'll often hear is this word, solvation. And all solvation is favorable interaction of dissolved molecules with a solvent. Okay, so that's kind of our first set of solvents. Our second set are the Lewis donors versus non-donors. So from this definition, right?
I have a question. Sorry.
No, you're all good.
On the previous slide, so the R group, we're assuming they're less electronegative than the oxygen, right?
Yeah, it can just be anything that's less electronegative. It can be a carbon, another hydrogen.
Okay, but in that case, would the partial positive charge be shared? Like, would the hydrogen be less partial positive because the R is also sharing that, or no?
Maybe, but just the fact of having that oxygen bonded to a hydrogen still produces a pretty strong partial positive on that hydrogen.
Okay, sorry, one more follow-up question. For the, like, you know how for bases, the more unstable, the better? So in this case, the more, I guess, I don't know what I'm saying. Thank you.
Okay. Okay. So our second set of solvents are going to be our Lewis donors versus our non-donor solvents. So donor solvents are going to be molecules containing oxygens or nitrogens, or essentially any atom that can donate unshared electron pairs. And so, in other words, these are molecules that can act as Lewis bases. So if you remember your Lewis base definition. Okay, and so some examples of these donor solvents are things like ether, THF, H2O, and alcohols again, right? And so this is what ether is going to look like, or I guess another alcohol depending on what that R group is. And this is what THF looks like. 5-membered ring with the oxygen. But the bottom line is that we have atoms in this molecule that are able to donate unshared electron pairs. And so the second part of that are these non-donor solvents. And those are molecules that can't act as Lewis bases. And so some examples of these are the common alkanes that we've been talking about. We also have benzene, which you'll get a lot more into in 3580. So that's just your 6-membered ring like that. We have dichloromethane, DCM. And then we also have chloroform. CH8Cl3. So then it's also interesting to kind of note that although chlorine has lone pairs, right, it's going to have 3 sets of lone pairs on it, because of how electronegative it is, it's not going to be able to act as this Lewis base. So keep an eye out for those kinds of halides that are too electronegative to act as Lewis bases.
What do you mean by Lewis base? Can you clarify that?
Yeah. So a Lewis base, right, is just any kind of molecule that is able to donate unshared electron pairs. Does that answer your question? So something like, okay. Okay, and then our final class of solvents are going to be our polar versus non-polar solvents. And so with this, there's so from what we know, right, we can classify solvents as having dipoles, but very specifically, when we're talking about solvents, our polar solvents are going to be what have dielectric constants of greater than or equal to 15, and our nonpolar solvents have dielectric constants of less than 15. And so what is this dielectric constant? And why can't we just say, oh, this solvent has dipoles in it, so it must be polar? Well, so this dielectric constant is going to be the interaction energy between two ions with respective charges Q1 and Q2 separated by distance r. And it is going to measure the ease of separating those charges. And so let's kind of look at what the equation for the dielectric constant is. So let's say we have something like E, which is just going to stand for energy in this case. And we do K, and then we do Q1, Q2, divided by this dielectric constant, which we are going to represent by this epsilon, by this Greek symbol epsilon, multiplied by r, which is going to be our distance. So this is the dielectric constant. And so let's imagine we have two charged particles. Thinking back to physics. So let's say this one is going to be negatively charged and this one is going to be positively charged. And the distance between these two particles is going to be r. And so the dielectric constant is just a measure of how well we're separating those charges. And so in a, let's put in examples for this. So in some kind of system that has sodium and chloride anions floating around, right, you're going to have this dielectric constant separating the charges, right? To a certain degree, these charges are going to be separated, but they're still going to be attracted to each other. So that's going to bring us to an important point, which is that the larger this dielectric constant is, the magnitude of interaction, so this magnitude of E, is small, right? As we increase that number, this is going to decrease in magnitude. And that's going to be because, right, the dielectric constant is just how well we're able to separate these charges. And so by putting in some kind of solvent into the system, a solvent that is able to stabilize, to solvate this Cl minus and this Na plus, we're going to be able to keep those two ions apart, and we're going to increase the energy of this system. We're going to decrease the attractive interactions that are going to happen in that system. So let's continue this. This means attractive plus repulsive forces weak, right? They're not going to be as attracted to each other anymore. And so the second point is that oppositely charged ions are going to tend to associate less in a polar solvent than an apolar solvent, right? Polar versus apolar solvents. Okay, so are there any questions on that, on the dielectric constant and polar solvents versus apolar solvents?
What is the polarity of the solvent due to the value of R?
Yeah, so in this case, R won't really matter, right? R is just going to be kind of the distance between any one of these solvent molecules. And so in kind of any system, you're just going to have a bunch of arbitrary R's as the molecules kind of move and fluctuate. And so no matter what, you're going to just focus on the dielectric constant, which is going to have a greater impact on the energy of the system. I guess if you maybe look closer into it, you might get like some change in energy by how far apart these molecules are, but you can imagine when you have some kind of container, they're all moving randomly, so R will be constantly changing between any two ions. Does that answer your question?
Yeah, that makes sense. So how did we find out that this dielectric constant was large again?
Yeah, so the dielectric constant was just something that was experimentally kind of determined. And so with the dielectric constant, right, with it being greater than or equal to 15, it'll cause this energy to be large enough for our solution to be well solvated, for those solvent molecules to be kind of interacting and stabilizing whatever we have in our reaction.
Okay, that makes sense.
Okay, and so then the last part of this is that all polar solvents are going to kind of consist of dipolar molecules, but not all dipolar molecules are polar solvents. And so let's kind of do an example of that. And so if we look at something like acetic acid versus formic acid, right? So I think we can all agree that both of these are going to have a dipole. But for acetic acid, our dielectric constant is going to be equal to 6.1. And then for formic acid, our dielectric constant is going to be equal to 59. So although both of these molecules have dipoles, right, only this one is going to be our polar solvent. Okay. And so my final point for today is that this is going to be important because our solvent choices are going to play a role in our SN1, E1s, SN2, and E2 reactions. And without further ado, I will let Brendan take over.
Okay, so I'm just gonna share my screen. Okay, so I'm going to be talking about solvolysis reactions. And so the reaction mechanisms themselves are going to look very similar to ones that you've already learned. We're going to be talking about like SN1 and E1 reactions primarily. But in this case, the solvent is going to be doing all the work, okay? And so Solvolysis reactions are the reaction of an alkyl halide with a solvent in which no other base or nucleophile is present. And so we're just gonna jump right into an example. Maybe we will. There we go. Okay, so for these examples coming up, we're going to be talking about the solvolysis of tert-butyl bromide, which basically looks like that. Okay, and so what we have is we have this is tert-butyl bromide, and we get the carbocation formation in the SN1 mechanism, right? So we have that in equilibrium with, oops, like this. Okay, so we know that for SN1 reactions, the first step is always the carbocation formation, and that's the rate determining step because carbocations are relatively difficult to form, and carbons prefer not to be charged. So the next step, okay, is we have that carbocation. And for our solvent in this case, we're going to use ETOH, right, which is just ethanol. And this ET is just stands for, it's like an ethyl group. And so we have the electrons on this oxygen coming in and attacking the carbocation and forming a new covalent bond, right? So we have CH3 connected to the oxygen with hydrogen and a plus one formal charge on the oxygen now, right? And don't forget, we always have the Br still floating around in solution. And so, as we know from previous reactions, oxygen doesn't prefer to have that positive charge. And so other elements, other molecules in solution will come and deprotonate that. But since the solvent is the only other molecule essentially present in solution, the solvent is going to actually be the one that deprotonates the oxygen.
Wait, what's our solvent again?
What's a solvent?
Yeah.
So it's basically what you're using to carry out your reaction in, right? So for example, if you have table salt, right? So sodium chloride, and you put that in water, right? And the sodium chloride dissolves in the water, right? The solvent that you used in that case was the water, right? The water is what dissolved the solute, which in this case is the sodium chloride. Does that make sense?
Yeah. So in this case, you said the OHET, that's the solvent.
Yep. So in this case, the ethanol is going to be our solvent. Exactly.
Okay. Thank you.
Yep. And so after a second molecule of the solvent deprotonates that, we get the final product of like this. Okay. Any questions on this reaction? Okay, so basically just to summarize this reaction, right, we have the tert-butyl bromide was in a polar protic solvent, right, because our solvent that looks like this is considered polar and protic because it has this hydrogen still attached, so that's protic. And so in that you form the carbocation intermediate, in which the bromine ends up becoming substituted by the solvent. And so the solvent that formed a new covalent bond with the carbocation is then deprotonated by another molecule of the solvent that you're doing the reaction in. Okay, and so again, this particular solvolysis reaction, it followed the SN1 mechanism. Okay. Okay, so for this one, we're going to look at solvolysis in an E1 reaction, and we're going to stick with our tert-butyl bromide as our substrate. So we get carbocation formation. Like this. And now if we remember from other E1 reactions that we've looked at, we're going to end up with the formation of an alkene, right? So we have like this. So we have, I just picked one of these carbons surrounding that central carbon with the positive charge, because each of them would be beta carbons in this case, and so the reaction would yield the same product, depending on like whichever carbon you chose. So again, for this one, we have our solvent being ethanol, and this is going to attack a beta carbon, which then donates those electrons back into a carbon-carbon double bond. Okay, and so we get the product as okay. Any questions on this? Okay, so again, we used the polar protic solvent. You get the carbocation formation, and the solvent then reacts with a beta hydrogen to form the alkene. Okay. Okay. So now, so today we're focusing on SN1 and E1 reactions, but many of the concepts are similar for SN2 and E2 reactions. Okay, so when you have, say, tert-butyl bromide in this polar protic solvent, both reactions can compete with each other in this solution, okay? So if we look at that, right, we have, sticking with our tert-butyl bromide, and so we saw the formation, well, we saw the elimination product, right? And we also saw the substitution product. like this, okay? And so in this case, the elimination product is 19% of the product's form and 81% substitution. Okay, so notice here that we have two substituents around the double bond. Okay, and so this will this kind of concept will come into play in the next example. Okay, so now we're going to look at, oops. Now we're going to look at this molecule. So we'll have CH3. Okay, and we'll have this solvent. And we are going to form a couple products, okay, which are, let's see. This one plus this one, okay? And so because of the beta hydrogens that were taken, all right, if we see this one is right here is only has 2 substituents around the double bond, whereas this one has 4 substituents, okay? And so this one right here is the major isomer that's formed because you have the 4 alkyl substituents at the double bond. Okay, and so this right here is the elimination products, and this constitutes 62% of this reaction. And we also get substitution products, which look like this. Okay, and so if you notice, we have, and oops, that did not work. The alcohol here and the ethanol, or the what was the ethanol here, okay? Because we have both H2O and ethanol in solution, so both of those things are competing for that carbon which had the carbocation. Okay, so both in this case are able to attack that carbocation. And so these 2 reactions constitute the other 38% of the products. Okay, so we have 38% substitution. Okay, and so if you remember from previous lectures, right, heat can increase the percentage of elimination reactions, and you can also, so solvents play a big role in the type of reactions, the that take place, okay? And also it's important to note that oftentimes the alkyl halide structure is, and the nucleophile strength have more influence on the reaction than the solvent, okay? So the solvent is definitely capable of influencing the reaction. However, depending on the structure of the alkyl halide, you are likely to see more of one or the other, depending on stabilities and things like that. So, for solvolysis reactions, rearrangements are also possible. And so we have something like this. And we get this product. Okay, so this group right here has been rearranged over here, okay? So when the chlorine leaves, right? Oops, I think I forgot a. So when the chlorine leaves, we get a secondary carbocation formed. And so with this methyl group, with this methyl shift, right, we then are able to create a tertiary carbocation on the next carbon over, and your ethanol and your solvent is going to then basically substitute at the that carbon in which the methyl group left, okay? And so just like in the other reactions you've seen, methyl shifts are possible to stabilize the carbocation in the reaction, okay? And some final points, okay? So SN1 and E1 reactions are fastest in polar protic donor solvents. So the polar portion of it, right? So we have a high dielectric constant, allows for separation of ions. And then the protic and donor portions stabilize both the positive and negative charges. And so basically what this means is the carbocation intermediate is stabilized and the halide anion is stabilized. Okay, and so this helps the reaction move more quickly. And so although we didn't focus on it today, I'll just make a note about SN2 and E2 reactions. So these ones you want their fastest in polar aprotic solvents. And so the reason for this is that polar protic solvents stabilize the nucleophile. And so let's just say if the nucleophile has, let's just say a full negative charge, right? If you saw from Correl's slide when all those molecules with the OHs attached, right? You formed either hydrogen bonds or dipole interactions. And so when that happens, when you have, say, hydrogen bonding, you're actually reducing its effective negative charge. And by doing that, you're reducing its nucleophilicity. Okay. And so we know for SN2 and E2 reactions, you want a strong nucleophile, right? You need a good nucleophile in order for the reaction to take place efficiently. Okay. So that's why you want, for SN2 reactions and E2 reactions, a polar aprotic solvent. So those hydrogen bonds are not able to stabilize the nucleophile. So the nucleophile can maintain its strength. Okay. And so the last thing that I'll show you is this kind of putting it all together table, which will hopefully help in your studying or when you're having difficulty deciding which reactions are going to take place. Okay, so if we look at this table, we see that it goes down for methyl as a primary, secondary, tertiary, and across the top it compares protic solvents, aprotic solvents, strong bases, and bulky bases. Okay, so just to do some examples, right? If you have your methyl, it's going to be SN2 every time. You can't have any of the other ones. It's not possible, right? But in certain conditions, you can have competing reactions, as we talked about, right? So if you look at the tertiary in the protic solvent, you have SN1 and E1 competing, or in the secondary and strong base, you have competition for E2 and SN2. Okay, so hopefully this table will help. And when we post our notes, there's also going to be some helpful tables in there. And there's also a helpful cheat sheet, which I took from my notes from 3570. So hopefully that will help. It really separates or helps you differentiate between different solvents, whether they're polar, nonpolar, protic, aprotic, that type of thing. So definitely check out the notes when we post them because there's additional material in there that will help you out for both exams during this course and come the fall. So yeah, we were actually able to get through this material quicker than either of us thought. And so that's all we have for you content wise today. So yeah, if you have any questions about anything, then feel free to ask. And if not, free to go.